Sorry.
Do you mind get rid of my cell phone?
Yeah.
Thanks. Thanks. Yeah.
No, well, I got very lucky in that I managed to get on a charter flight. Once I was at LaGuardia, I got standby for I was supposed to get it at midnight.
But a week before there was a similar, my colleagues were stopped.
Just go ahead and stop.
Yeah, why don't we start?
Good. Okay, welcome back. Today I want to continue the discussion from yesterday, and I want to start with a very brief recap of some of the key findings from yesterday. So one key thought was about how to compress quantum many-body states, and we now just very naturally use this diagrammatic tensor representation, which you also saw in the previous lecture. So now our many-body wave function corresponds now to an order L tensor. So it's a blob with L legs sticking out. And we found that if the state fulfills the area law entanglement scaling, or like have an area law entanglement, then we can find a good approximation of the state in terms of a matrix product state. Right? So now we decompose this order L tensor into a product of L order 3 tensors. At this stage, it's generically an approximation. There's a bunch of states that can represent it exactly in terms of MPS, like this GHZ state or the ground state of the AKLT Hamiltonian, but generically this is an approximation. Now, every matrix product state can be exactly rewritten in terms of this canonical form I introduced. And the canonical form is that we have rank or order 3 tensors gamma relating the local and the Schmidt basis, and we have diagonal matrices containing the Schmidt values. And in this representation, we can now very efficiently or simply calculate local observables, as I showed yesterday, by using the fact that the transfer matrices have dominant eigenvectors, which are the identity. But which I find also nicely to illustrate this representation is that we could say that, well, if we are contracting all the tensors up to a given bond, so we stop here after this gamma, then these are now the left Schmidt states. If I contract everything right of a given bond, then I'm getting the right Schmidt states. And then I have here the corresponding Schmidt values in between, right? So if the state is given in this form, without doing any calculation, I can now get the Schmidt decomposition for a given bond. Good. So this is one thing that we discussed yesterday. And another thing that I'm going to make excessive use of is that we can take the time evolution that we might be interested in and decompose it into this brickwork circuit. And what I want to show now is how we can efficiently apply this brickwork circuit to a state, right? So now that what we want is we just have now a wave function psi given in terms of an MPS, and then we want to evolve this wave function by this operator, which is now just applying this brickwork circuit to this MPS. And from this construction, you can see that this technique is not only useful for working with Hamiltonians that we want to evolve, but it would also, if you have some specific random circuit or not so random circuits, if you have like, or Fouquet circuit, if you have some circuit and we want to evolve it, we can use exactly the same technique. And the key thing, and this is what I want to discuss now, how do we actually then get back to a state, right? So this is what I want to discuss. I already started briefly the strategy, because the strategy that I want to follow is that I'm saying that, well, I'm just sequentially applying these two-side gates. So we start with maybe one of them. You could start applying this one and then compress it back, then move to another bond, compress it, and move to another bond, and so on and so forth. So the core thing that we need to figure out is that we are now taking a matrix product state, or like the two matrices on which our gate acts, and then we need to compress it. So we just start here from a state where we have some gamma and lambdas, and now we need to compress it to some new state, which is given by some gamma tilde and lambda tilde. Right. So this is now the task that we have to do. And to understanding why this works, we can actually just recall again a nice property of this canonical form, because now if I just take my MPS and I cut out a block maybe of this form as I've done here, then the contraction of those tensors, I mean, which now give me an order 4 tensor, that these are now the amplitudes of the full many-body wave function in a mixed basis, right? So we still have a wave function that is defined on the full, on our full system consisting of L sides, but we are representing everything left of our two sides in terms of the Schmidt states to the left, everything right in terms of the Schmidt states in terms of the right, and then the two sides that I want to evolve is now represented in terms of a local basis. But you see, in principle, if we just multiply more and more, we can actually just interpolate between a representation in terms of Schmidt states and the full representation which we would get if we actually expanded up to L sides. But then there's no gain from this technique anymore. So the core question we have to answer is how to do this. And this is now done by the TEBD, or time evolving block decimation algorithm, as introduced by Giffre Vidal in, I think, 2003. And now what I want to do is I want to go through the steps of this algorithm. But before this, other questions about this recap? Yes? Which approximation? This one? The contract is, there's a paper by Norbert Schuch and others from 2006, and they actually rigorously prove that this works.
Like the fidelity?
No, the fidelity, right? So the fidelity of the state is of course 0 because it goes exponentially 0 with L. But you can prove that if you have an areolar state and compress it this way, that it has a constant energy density. Sorry, a constant error density. Good. So let me now introduce the TEBD algorithm. Right. So this is now the TEBD algorithm, and it basically consists of four steps that I want to align here on this slide. So the first step is that we are now going to this mixed representation of our state. So the step is that we just now saying that we are contracting gamma, lambda, gamma, lambda, gamma, and let me just label them. This here is C. This is B, C. A, C. Right. So because for a generic state, all of those gammas and lambdas can be different. So I'm just labeling them as with A, B, C. And so I'm contracting them. So now we have here an index alpha, gamma, and then we have here m and n. And now this is now we can just contracting them to a blob, and this blob I'm calling theta. So now we have contracted all of them, gamma, alpha, m, n. And now these are the amplitudes of the many-body wave function in this mixed basis, as I just mentioned on this board. So it's just exactly this kind of mixed representation of the state that we get. Now, in this mixed representation, I can now apply my gate. Right? So now what I'm doing is I apply the gate, and which means that I'm going from my theta to theta tilde, and my theta tilde, which is this object, is now given by my theta, where I just contract this one gate to it. So this is the first step where I'm actually doing the time evolution of my state in this mixed basis. Now I want to start my work to get back to this representation of my wave function in terms of an MPS. And for this, what I'm doing is now the second step, which I'm labeling as the singular value decomposition step. Right? Because now I take my object, which I might take now my theta tilde, and my theta tilde is theta tilde. So I have my theta tilde. My theta tilde is now an order 4 tensor. But now what I can do is I can just group these legs together. And so now I can also see my order 4 tensor as being a matrix. And the matrix has now a dimension of d times chi and d times chi, right? So just by merging these indices together, now I get a matrix of the dimension d times chi. And as before, when we motivated this canonical form, what I can do is I can now do a singular value decomposition of this matrix, which corresponds to a Schmidt decomposition of my state at this new bond, right? And this is a interesting thing to do, because this unitary changed now the entanglement structure across this bond. Right? Since it's a unitary, it didn't change anything elsewhere. It only changes the entanglement across this bond. So now we can reevaluate the entanglement that we get at this bond by doing a Schmidt decomposition or a singular value decomposition. So now, if I'm doing the singular value decomposition, then I have now my x. Now I have the lambda tilde, right? Because these are now the new Schmidt values, which likely have changed by applying a unitary on that bond. And then we have here y. Right? So these are now two unitaries, like unitary x, unitary y, and we have now the singular values or the Schmidt values in between. And now if I think in terms of my bond dimension, so the bond dimensions that I have is here chi, here it's chi, here we have d, here we have d, but in between, the bond dimension is now d times chi, right? So recall these are x and y are unitary, so they must have the same dimension on the left and the right. So now we have something with an increased bond dimension. And this is not yet quite our gamma lambda form that we are interested in, but we still have this lambda A and lambda C multiplied to the left and to the right. And because the unitary only changes the entanglement or the Schmidt spectrum on this bond, the lambda here and lambda over there, they are unchanged. So in order to get rid of them, we just have to multiply with the inverses, right? So now we have the third step, which is we can call it obtain the new MPS. And that step, I'm now taking my MPS and I'm just inserting an identity. So I have here my X, lambda, Y, and now I just insert here a 1. So I have my A, lambda A times lambda A inverse. And then from the left, I have my a lambda C inverse lambda C. Yes?
Leave the lambda A and C out at the beginning.
Oh, that would be a bad idea. Because I want the right. So this is actually a good question. So when so far there's nothing that would have gone wrong. It will actually go wrong the moment that we do the truncation. But let me talk about this maybe at that moment. But keep this in mind. Yeah. Yes.
Clarify. Your SVD is this theta or theta tilde?
Oh, this is a theta tilde. This is the one where I applied my U. If I would take the theta, I wouldn't have to work very hard, because then we know that there would be the lambda as before. Yes?
Find the leg, add the then put the leg back to the forward.
You mean when we do the combining and
Find the leg from forward to
yeah.
add the then put the leg back to forward.
Oh, this is just a simple reshape. So because we still know exactly how we did the reshaping, so then we also can undo it.
Is there not some arbitrariness in how you do this?
There's an arbitrary. You have to do it in the same way, right? So basically, if you have a let's say that you have a two-dimensional space given by X and Y, but now you can just represent it as that. Let me just map this now to one-dimensional space. We say that, well, we have X times plus, I don't know, some whatever quantity like times Y, and then I just need to keep how I basically map some two-dimensional space to a one-dimensional one. Yeah. Good, right? So we just use this mixed representation, and here again I've chosen this because I want to have it like if I choose this form as I've chosen here, then I actually have my theta here correspond to the amplitudes with respect to an orthogonal basis, right? So as shown up there, then I'm doing the SVD to get my new lambda tilde, which already signal how the entanglement structure has changed by applying my U. And now I want to just illustrate how we can get back exactly the form that we got, and I can just do this by inserting now these identities. And from this form, what I find, and maybe I do this in red or in orange. So now my theta tilde, where I have here now a big bond dimension, is equal to my X, where I'm applying here my lambda A inverse. And then I have my, I'm sorry, so here this is my B. And then I have my gamma tilde C, where we have a big bond dimension here, is equal to my Y, where I'm applying here a lambda C inverse. And we've got the new lambda tilde, which is exactly the one that we get from here. And this also has a big dimension. Good, right? So now we returned to the form, and you can convince yourself that after doing this, you just have an MPS which fulfills the canonical form. So in this respect, all is good. The slight issue we have is that the dimension here has now increased from chi to d times chi. So if we keep doing this, we would find that the bond dimension will increase exponentially as we go along. And then this is not what we necessarily want. So but now, since we just obtain the Schmidt values, we can actually see how much each of those Schmidt states contributes. And if we plot now the lambda alpha as function of alpha, and as we discussed yesterday, we sort them according to the size, it might look something like this, where we have here chi, here we have d times chi, and now we can actually see, so one thing, we can now stick to this bond dimension chi. We could say that, well, we only keep exactly these chi states and we just throw everything here away. But if we see that there is too much, we can also say that, well, at this stage, maybe we increase to some chi tilde. So we increase our chi a little bit to actually also keep these states which are somewhat large. And then we can ensure that we are doing a good job in doing the evolution at this bond. And the error that we are making at this step is given by the truncated wake. So whatever we are throwing away, this is the error we are making at this single step. And if we find that whatever we are throwing away at this stage is close to machine precision, then we don't worry. And now this is actually the point regarding your question, why it would be a bad idea to not put these lambdas here. Because if we don't put these lambdas here, well, we would have to put them here. So basically then we would not have a representation with respect to an orthonormal basis. So something might have like a very small factor here, which gets a larger factor here or vice versa. So basically, if we then throw away the small Schmidt values, then it would be the optimal choice for truncating it with respect to this coefficient matrix theta tilde, but that might not be the optimal choice for the actual wave function, right? So then it would be locally optimal for this theta tilde, but not for our wave function, because what we actually want is that we take our psi tilde minus psi tilde, I don't know, truncated. This is what we want to minimize. And only if this is an orthonormal basis, this is actually the case, but when doing this truncation, right? So we do not want to leave out these. It's fine if we don't truncate at all. If we just keep all the states, it's good. But this is what we usually want. So it's very important to leave this lambda where it is. Yeah. Right. So as I shown in this recap, right? So basically, you have these lambdas, and if you just if you contract everything left of this lambda and everything right of this lambda, you're getting the left and the right Schmidt values respectively. Yes. For a single step, yes. Like if you just do a single step, then the error exactly corresponds to what you are leaving out here. But it's impossible to rebound it from above if you keep going, because if you're just truncating on one bond, then the error will continue. So you don't know where things are going. So, but the safe thing to do is that you just making sure that at each step you just hardly truncate at all, and then you are good. Good. And now we have an algorithm that allows us to apply 1U, and then now we can just apply the same algorithm over and over again to actually apply our brickwork circuit to a state, and by this do the time evolution with respect to some Hamiltonian using the trotterized form, or do it for some random unitary evolution, etc. And let me just now make one more point in terms of like how, and this is like an important question for all sort of tensor network based algorithm, is how these algorithms scale as function of system size, as function of the bond dimension, etc. And now what you can do is you can go through each step and figure out how expensive a given step is, I'm not doing this for all of the steps. I just want to just quickly show it for maybe just a few steps. So we could first start, well, if we contract our tensor, so if we, for example, have our tensor gamma here, and we want to contract it with the lambda tensor, the way that we can evaluate how expensive it is that we are counting first the legs that we are left open, so which is this guy here. So we have a chi here, we have a chi here, and then we have a d here, which is open, and we are summing over a leg chi. So we see that this whole operation scales as or the number of iterations we need to do for doing this contraction is scaling as d times chi cube. And then you can just go on, like each iteration, you can now figure out what the cost is, how it scales by just counting the number of, just keeping track of the number of open legs and the legs that you actually contract. And for this TBD algorithm, you actually find that all the steps for the contraction scale as most as bond dimension chi cube. And the most expensive part, actually, which is the singular value decomposition, the singular value decomposition of a d chi dimensional matrix scales as d chi cube, right? So the SVD also scales as d cube times chi cube, and then we have to do this for every site. So it scales as L times d cube times chi cube times the time that we want to evolve it, right? So good. So there are many more things and many more details that I could tell at this point, but I'm not. But I mean, I put a few more comments in the lecture notes, and you can find on the literature. But let me now quickly show how this algorithm can now be implemented and show it in action. So now I already showed this Python script yesterday. So the first bit, we had now a bunch of functions which I already went through. So we can initiate a simple product state, which is easy. We can initiate the bond Hamiltonian here. Here it's for the Ising Hamiltonian, but that could also be something we use for random matrices. So you could just use a H random U here or whatever you like. And then we have these functions calculating expectation values for bonds and for sites using the canonical form, the entanglement entropy. And now here you see now the Python implementation exactly of these 4 steps that I just showed diagrammatically. So first we are, right? So here actually one thing why is it always flipping back? So the B here I introduced is the B that I have in this code corresponds actually to gamma times lambda. So I just keep them multiplied for the reason because I can, then we don't have to always multiply these gammas and lambdas. So if you just see a B, just keep in mind that this means that we have just the gamma already multiplied with my diagonal matrix lambda. So I just get my state. I'm multiplying the U to it. I'm multiplying the S. So then I get this theta tilde as I had in these diagrams. And now I'm doing this reshaping to just transform this D times chi, the D chi, to transform my tensor into a matrix by just merging these to a matrix. On this matrix, we do the singular value decomposition, and then we just do the truncation, and then we just multiply with the inverses as shown on the left. So then we get all we need, and now we can play around with it. So now one thing that we can do is we can do imaginary time evolution to find a ground state. So you wrote a function which is this TBD Ising ground state. So now what it's doing, it's just doing iteration. So it just keeps applying it's doing imaginary time evolution with a decreasing time steps. And this is so it just successively reduces the trotter error. Right? So basically if I do imaginary time evolution to find the ground state. So I just write here the energy as function of imaginary time. I'm first doing rather large steps, so it just converges quickly, but it will converge to some value which has still a fairly large Trotter error. Right? So I do this here maybe with my delta tau equals to 0.1. And now, after a certain time, I then reduce the time step, and then I'm doing now this in smaller time steps, and then even smaller time steps, etc., to converge fairly quickly to the optimal state. I could have already started with very small time steps, but then it would just take longer. So that's just a simple trick to get this to work. And then I have another code here, which is doing just the time evolving, like doing a sort of quench dynamics. We just start from an MPS, and it's literally doing what I advertised on the left board. So then we have these functions. Now we can play around with it. So for example, we can now use these code to find here the ground state, or approximate the ground state of an Ising chain with 8 sides. So we see here in the time that it was ran, it just converged pretty well to the exact ground state that we can get from exact diagonalization. Or we can do now the time evolution of a quench. So we just do a global quench, and then we can also see how the truncation errors, etc., plug in. So here I'm doing just a quench with the Ising Hamiltonian, and we see at the bottom plot the entanglement the half chain entanglement entropy, and we see that, well, first for a very small bond dimension, it first shows the linear growth, but then it saturates to some value, and this is due to the truncation. And then if I increase the bond dimension, well, I see it just follows the other one before, but it keeps going for longer. And this is also like a way, if you see the data, the moment that stuff starts to deviate for the entanglement entropy, we should then be careful about the data. So then we just need to increase the bond dimension. And accordingly, we see also this for the energy conservation. Once we truncate too much, the energy conservation, which we should have under unitary time evolution, is no longer obeyed. And then you can also look at some observable, for example, just at the expectation value of C or whatever, right? But the important takeaway message from this is that we really have to watch out for the bond dimension, because if it's too small, then we're getting results which are not working well. And lastly, we can also just combine imaginary and real-time evolution. We can, for example, find an approximation of the ground state, for 21 spins, and then flip a single spin and then look at how the entanglement spreads. And now we just see this light cone picture. Right? So here we just start with the ground state, we flip a spin, so this creates locally an excitation, and now we can just track how the entanglement grows in the system, and we see this light cone. Right? So already with these kind of fairly simple tools, and the key is really just these kind of 10 lines of Python code allow you to now study dynamics in fairly large systems. And we are now not limited by system size, but we are limited by the amount of entanglement in the state. Yes? Oh, yes, thanks. So the way that I'm advertising it here is in such a way that we can do this all without having to truncate. But indeed, if we start to truncate, this would destroy the norm. So if I have my Schmidt spectrum, so I know that my Schmidt values alpha, if I'm summing over alpha, alpha squared, this should be 1 for a normalized state. If I'm throwing away, let's say that here I'm sticking to my chi and I'm not increasing it to a larger value, well, then I will destroy the norm of the state. So the norm will be smaller of the state. And what I'm doing at this step is that I would say that, well, I basically renormalize so I would just renormalize these gamma tilde. I just divide it by, so then I would just divide this by the sum of lambda alpha squared from alpha from 1 to chi. And then it's renormalized. And then, as I said, I mean, there are many details which I put a bit on the rug. One of course, like the moment that I start truncating, I'm also messing up this canonical form. And if I'm say that I did a truncation on this bond here, and thereafter doing a truncation on a bond here, then it's not necessarily optimal more. So what I would have to do is basically, whenever I truncate, I would have to bring the full state back to this canonical form before I move on. But in practice, you just, at each step, you just do very little to almost no truncation, and then there's actually no reason to worry about it. So the improvement by doing this extra work is negligible. Right. So the and maybe it's like easiest to see in this one, right? So here, the moment that I have if I have my state being perfectly in this canonical form, then as I advertised, we can now contract all the tensors up to a given bond, and then these are now the Schmidt states. But now let's say that we are at, let's take exactly this example. If I did now some truncation on this bond here before, then contracting it all here, this is not necessarily the Schmidt state for the next bond. Right? So basically, if I'm doing an error of 10 to the minus 8 or something on this bond, then this error will carry over, and we won't have the perfect or not the optimal solution for the next bond when we do the truncation. It's like, as long as we don't truncate, that wouldn't be any issue. But the moment we truncate, we might not truncate in the optimal way. Yes?
That while I'm speaking through the shape, say at stage 1, I do something, I truncate, I find some chi-tail level. Next one, when I do it, I can still get a chi subprime.
That's right, yeah.
So at the end of a sweep, I have at every point different chi that is.
Potentially, yes.
Practice to put it back, or is this keep it as is? So what's the bond dimension that is worth at?
But that depends very much on the problem. And if in the extreme case, you might have a dimerized model, and you might find that there's a larger bond dimension on A bonds as on B bonds, or vice versa.
Look at a usual model with maybe of this chi won't fluctuate, they won't fluctuate much at a particular speed at a particular time.
No, right. So no, but you might like so if you like, for example, look at ground states, you might find that first the chi increases, but then it converges to a fixed value.
Chi as a function of time, I can understand.
Yes.
At a particular time, to the lattice, I can have chi different at every lattice point.
Yeah, but these are different states. So you just first do it maybe between these guys here. You have a given bond dimension, and there are certain restrictions on like how the bond dimension can grow following subadditivity, etc. But besides this. Oh, well, I mean, like what I usually what this code does, it just keeps increasing the bond dimension up to a hard cutoff, right? So I'm saying that, well, I have my somewhere here, maybe I have my chi cutoff, and I'm not going past this. And then I just can kind of vary bond dimension, and then there's this hard wall. And I want to have this hard wall, because if I don't have this hard wall, then my computer might crash because it uses gigabytes of memory eventually. Yeah.
Sorry, maybe I missed this point. Like when you say that you don't, the norm is not maintained, but you're actually renormalizing the singular values by the with the truncated state.
Yes.
Right. So it's a norm 1 state.
Right. If I just do this, that's why Anushya asked, I think, because in the way that I set it up here, I didn't say anything about renormalizing it, because I said, well, here I just hardly truncate at all. But if I do truncate, it's actually important that I renormalize it at this state. And this is also done in the code. If you look, there's a line somewhere. So here is C. So here I'm renormalizing it. Yeah. Yes. Yeah.
Sorry, is this like the analog of setting your orthogonality center in DMRG?
Yes, actually, I'm going to explain DMRG in exactly the same language in a moment.
But for the canonical form, it's like you're doing that along, right?
Well, there's a.
But I mean, in DMRG,
I mean, this.
In DMRG you have to update it on which site you're at. But
Yeah, no, but there's a slight difference. So there's like usually when you have a DMRG code, you might just use an isometric form, which is a less rigorous requirement as what I'm having here on this canonical form. And basically the cool thing here on this form is that you cannot randomly pick a bond and then your orthogonality center is at that bond. But for this less rigorous canonical form, like for this isometric form, you actually need to shift it back and forth. Yeah.
Right. But when you're moving through the chain, you might, if you're actually doing a decimation, you might need to do this, like set it in the isometric form.
Right. Good. Yeah. Uh-huh. Okay, so yeah, indeed, there have been various improvements or also other algorithms, but in terms of performance, I think this is still a pretty good algorithm. So there are now, so I would say that if you have a Hamiltonian, which is of this form where you have, as I pointed out here, like if you have a Hamiltonian which you can easily trotterize in this form, probably TBD is the method you would choose even today. But then there are a bunch of other methods. I mean, one, for example, there's this called of time-dependent variational principle, which is a method that allows you also for long-range Hamiltonians. And there's another method, which is some matrix product, right? So there's a way that you are expanding this not in a trotterized form, but you are writing the time evolution operator in terms of a matrix product operator. I'm going to explain in a moment what that is. That's also allowing for long-range interaction, and that might be beneficial in some other cases. And then there are also lots of technical improvements. So for example, if you want to use GPUs instead of CPUs, then there are smarter ways of doing this. So you can make this TBD more efficient by replacing SVDs by QR decompositions. There are lots of tweaks that you can do, but I think that, or in general, I would propose, like, if you have a problem where you think matrix product states might be useful, I think it's always a good idea to first implement this extremely simple algorithm, which takes these 10 lines of Python, and see how far you can get. And if you're running into a hard wall, then think about what kind of technique might help to push it a bit further. But like also, like, one comment to this also, if you, for example, look at non-equilibrium problems, like these quench problems, etc., the linear, like there's this linear growth of entanglement and thus the exponential growth of bond dimension. And that's why even if you make your algorithm twice as fast, it just gets you half a time step more. So, yeah. Yes?
There a way of thinking about the time evolving block decimation as framing these prioritized evolutions as ideas, just like 2 seconds ago?
Well, the thing is that if you have, I mean, but yes, you can write it in this form, but then there's no gain from that.
Yeah, maybe just conceptual.
Yeah, conceptually yes, but it's no right. Yes.
So how do you write the unitary operator? Is that generally doable, or?
Yeah, I mean, there's a paper actually which we wrote together with Mike a couple of years ago, and there's an idea basically. You do a local Euler step. If you're saying that you're expanding, let's say that you have some Hamiltonian of local terms. If this is your Hamiltonian, then you can take your e to the I h times some delta t. You can basically write as a product over 1, like the sum over all sides I, the sum over 1 minus I times delta t h. You can do this kind of local Euler step, and this one here you can actually show that you can approximate in terms of an MPO. So, but that's another method which is a bit more involved for applying it. Good. So what I want to do next is I want to explain the density matrix renormalization group method. And maybe like just a quick historic note. So the DMRG, or density matrix renormalization group method, was there before people connected it to matrix product states, and it was Steve White came up with it in the early 90s, and he came from an RG approach. So basically, there are certain problems where numerical RG didn't work well, and he then thought of this density matrix renormalization as a way to do a better truncation. So that's why the name. But the way that I want to phrase the DMRG method is now I want to just use exactly the same language that I used for the TBD algorithm. So it's the same algorithm, but just formulated in a different way. So let me now maybe remove this. And now have the DMRG algorithm. So and for this, we need to introduce one concept that you already heard before. So far, what we did is we had MPS. And MPS, remember, we have just a blob with a bunch of legs sticking out, and we just approximated in terms of an MPS. Using the same notation, we can just also express operators, right? So let's say that now we have an operator. Like we have an operator acting on the same vector space as where our states live. Now this is a blob where we have legs sticking out at the bottom and legs sticking out at the top. Right? So the unitaries that you've seen in previous talks are a special form of this. But now, well, certain operators we can also now exactly write in this form, right? So let's say if you just using the same notation. So here we just expanded our state into a product of order 3 tensors. But now we could also say that, well, let us now think of our operator as being a product of these order 4 tensors. Like after I contract all of these tensors, I'm getting an operator back. Right? So in this more general form, I could say I have an operator given with respect to a certain basis. I can just write it like I1, I2 up to IL. This is now one index, and then we have the other index I1 prime, I2 prime up to IL prime. So these are now my operators acting on states in this vector space. And now I'm just writing this as some M1, which has now 2 indices, I1 tilde times up to ML, IL prime. So in fact, at this level, we can also, and I think, yeah, Saga also mentioned this, if we just bend up these legs, we can actually see that this is obviously the case, because then we're just bending up the legs, we are just turning basically the operators into states of a larger Hilbert space, where we have here a d-dimensional space, and here we would have then a d-squared dimensional space. And following, we can just use also the same strategy to transform any operator into a matrix product operator by, for example, doing successively singular value decompositions to turn it into an operator. But the price that you pay for a generic operator, the bond dimension required would be exponentially large for expressing it. But similar to the story that we had for MPS, we are also in luck that certain operators can be very nicely written in terms of very simple matrices. And just to give you one example, and this is example, we could now take the transverse field Ising model. So if we have H, which is minus J times the sum over sigma Zi plus 1, plus G times sigma Xi, right? So this is now the Ising model. And now I'm claiming that this operator can be represented by a very simple MPO. So the matrices M that I'm choosing. So this is M, which has as an index I, let's say IN prime, and then we have alpha, beta. And the way that I'm writing this is now I have a matrix. Here I have my index alpha and beta. And now I'm just putting here 2 by 2 matrices inside of this matrix. So the entries of this matrix are now 2 by 2 matrices. So I put here an identity, then I put here sigma z. Here I put G times sigma x. Here I put sigma z, and here I put a 1, and here I have minus j. And all the other entries are just zeros. So now if I choose this matrix and I now multiplying these matrices, I get back exactly this Hamiltonian. And let me just show how it works. So I first also, as in this form for the matrix product state, I need to just multiply on the left a vector, on the right a vector to actually get it to a proper operator. And now if let me just write it down here for a case of L equals to 3. If I have L equals to 3, then I have here 1, 0, 0. This is my starting vector. And now I put here my matrix M, N, N. And then I just terminate here with 0, 0, 1. And now the matrix multiplication that I choose here involves now the tensor product of the entries of the matrix. And I'm not doing this step by step, but if you're just multiplying it out, what you are then getting is that this is then G times 1 tensor dot 1 tensor dot sigma x plus 1 tensor dot sigma x tensor dot 1 plus sigma x tensor dot 1 tensor dot 1, and then minus j times sigma z tensor dot sigma z tensor dot 1 plus 1 tensor dot sigma z tensor dot sigma z. So then you see that just by multiplying these matrices, you get exactly the transverse field Ising model on a system with 3 sides. Yes. Yes. Yeah, right. I mean, I'm not going to get into details right now for the time, but there is a nice way to interpret the structure of matrix product operators in terms of finite state machines, which you know from engineering. And this is basically the way that you just design a machine to say that, oh, now place maybe a sigma z operator, and after you place the sigma z operator, then put a bunch of identities to then put a sigma x operator, etc. And then you're just running this machine over all possible instances, and this gives you then exactly this machine. Yes? No. So I mean, one way to see it easily is you can just again use the same gauge degree of freedom that we used for MPS. Yeah. Right, so you can. There are also there are techniques how you maybe you just come up with a stupid guess, then you can compress it if there's a more efficient way. Yeah. So there are lots of tweaks also for finding a good MPO representation. Also, you might want to approximate it if you, for example, have some long-range interactions. You can, I mean, using these MPOs, you can play lots of tricks. So, for example, if you have something like this, you have 1 sigma x 0, and now you just put here some eta, and then you have sigma x, and then you have here maybe a 1. Then this would correspond to exponentially decaying sigma x terms, which you can say. And so then you could say that, well, now it's very easy to write on exponentially decaying interactions in a Hamiltonian. Now you can just approximate, for example, a power law decay of interaction as a sum of exponentials. So there are lots of things to tweak, basically. Yes?
Is it always the case that for local interaction, you can always write it with finite
Yes.
dimension out?
Yeah. Can come again? I didn't hear it. For periodic boundary conditions, for the MPOs, it's not a problem. I mean, like, everything that I'm explaining here can be done with periodic boundary condition. It just adds a layer of complication. So these methods, DMRG, etc., they're much more efficient for open boundary conditions, because then we have this nice canonical form and everything is very well defined. For open boundary conditions, for periodic boundary conditions, you can do the same things. Everything works through. It's just getting more entangled and a bit more complicated. Yeah. Good. So now we can represent states in terms of matrix product states and operators in terms of matrix product operators. And now we basically have all the tools that we need. So now let's say that we have our Hamiltonian expressed in terms of an MPO. Now we can calculate the expectation value, like the energy, as the expectation value of our Hamiltonian, which graphically speaking looks now something like this. So now this here is the MPO of our Hamiltonian. These are now, right? So here it's maybe psi. Here is our Hamiltonian, and here is. And now the basic idea of DMRG is the following: we just first take the best guess we have for our state psi, and now we want to minimize this expectation value, and we will do it sequentially. We just first take out maybe two matrices. We just take out two of these matrices, and now we want to find a better guess. And I'm taking out to make it exactly in the same way as we did for TBD. So basically, if I just think about my blob, so what I want to do, I want to find a theta tilde, right? So if I just take these out, I multiply them, I get my theta, which is just a representation of the original wave function. But now what I want to do is I want to find a theta tilde, which actually gives me a lower energy. And this I can do at this step. I just take them out and I just find now the best theta tilde, which gives me now the lowest energy. Previously, we said that, well, we get a theta tilde by just applying a unitary gate u to this theta. Now I'm having a different objective. I'm saying that, well, I want to find a theta tilde by minimizing this expression. And then you see that, well, at this stage, after I found my theta tilde, I can just play the same game what I did for the TBD algorithm. I can then say that, well, from my theta tilde, I can then do the SVD and so on and so forth. So let me just explain how to do this minimization step in a bit of more detail, because this is the only step that's different from, like, there's only one step different, and all the other steps are identical to the TBD algorithm. Yes?
Is there any reason why we look at two sides at once?
Yes. So the one reason is that I want to just formulate it in exactly the same way as we have TBD, because I find this useful to just see that these algorithms are really on the same footing. And there are also various technical reasons for having two sides instead of one side. And this is because if you have two sides, you can grow the bond dimension, right? So basically you see that if I doing the SVD of my two-side wave function, I increasing the bond dimension from chi to d times chi. And this way you can just iteratively, like in a controlled way, increase the bond dimension. If you would do a single side update by just only taking out one, right? So if you just take out one matrix here, basically, then you would see that, well, this is a chi d matrix, and then you just wouldn't increase the dimension by doing this optimization. Yes?
Maybe as a related question, is there ever any benefit to doing like a three-side update or more?
Yeah, right. So this is these are all kind of technical issues, but yes, in certain cases, even if you're just doing a two-side update, you might not build up enough entanglements. There are certain scenarios where this two-side update wouldn't be enough, but yet then there are other methods to just grow this bond dimension in a controlled way, like some sort of controlled bond dimension schemes. But, yeah. Yes. 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 Right. So the thing is, like, if you're having, not only if you have two-side interactions, but let's say that you're having long-range interactions. Let's say that even you have interactions where you say that you have maybe sigma x, identity, 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 sigma x. Like if you have some sort of long-range interactions of this form, even in this case, this kind of update might not converge. But as I pointed out, the better approach to remedy this problem is not, one option to remedy this problem would be to have like a large n-side update, but this will be very expensive because the cost is growing exponentially with the number of sites that you include in this update. So the better way is to mix in states using using techniques which I'm not explaining here right now, but there are techniques to overcome this problem by basically mixing stuff into the density matrix. By basically applying the Hamiltonian to the density matrix by this mixing in relevant states. But this is a technical detail. Yes? Well, the one-side update is always more efficient for each step because it scales, as I said, the complexity of each step scales actually with the number of, exponentially with the number of sites that I include in my gate. And the single site update is numerically more efficient, but it might misstate. So to have if you really want to kind of optimize the DMRG code, what's often good is to find a good way to expand the bond dimension using, for example, this trick that I said by applying the Hamiltonian MPO to the reduced density matrix and use a single site update. Yes? No. This is also one thing that I haven't discussed, I won't discuss at all in this class, is that if you have a Hamiltonian which has conservation laws, for example, particle number conservation, or it might have an SU2 symmetry, there's a way that you can use a block diagonal structure of the tensor. So every tensor that you will have has then certain quantum numbers like n alpha, n beta, or n gamma, and ni. And if you have quantum numbers, you can then implement the algorithms to always just work in a sector with given quantum numbers. And that works for all of these algorithms, and we don't have to worry. Good. So the key point I want to make is that the DMRG algorithm is now a variational algorithm where we just now sequentially just take out matrices, improve them, put them back in, and then move to the next bond. And here, what we see, like this kind of optimization problem, we could just do very generally, but we can also just use now this canonical form to not have to solve a generalized eigenvalue equation, but we just can map it to a simple eigenvalue equation by using the canonical form. And this is like, we just have the first step is now our two-side optimization. And basically what we're going to do, and now I just, let me just draw the picture, but now being a bit more careful about the canonical form again. So let us say that we are now taking out here two sides, and let's say that we have here some gamma, and then we have here also my gamma, lambda, gamma, lambda, gamma, gamma star, lambda, gamma star, gamma star, lambda. But now we see that what I'm actually doing here is that I'm now projecting my Hamiltonian onto the Schmidt states. Right? So here, this MPO in the middle, this is my Hamiltonian. And now, if I'm just contracting all the tensors up here, as I argued previously before, we now have here some index beta. So these are now the Schmidt states beta. And then if I contract everything from the left, I got the Schmidt states phi alpha. And here we have now an index m and n. And then here we have alpha prime, beta prime, m prime, and n prime. And now this is now a representation of the Hamiltonian in terms of this mixed basis. So now I have a matrix representation of my Hamiltonian as alpha, m, n, beta, and then alpha prime, m prime, n prime, and beta prime. And then now what I have achieved is that I have now my Hamiltonian in a my Hamiltonian acting on my states in a mixed representation, where as before we are saying that, well, everything on the left is expressed in terms of Schmidt states phi alpha, everything on the right is expressed in Schmidt states beta, and we have here states m and n. Right? So this is now a representation of our full Hamiltonian in terms of a mixed basis of Schmidt states and local states. And now, since this is a Hamiltonian with respect to some orthogonal basis, it's now very easy to find the ground state. We can now use a Lanczos algorithm or whatever favorite algorithm you have for finding the ground state wave function. So now we call it theta tilde 0, because this is the ground state, and this is now E naught times psi naught. So now, just by solving an eigenvalue equation, just by iteratively finding the ground state of this Hamiltonian in this mixed basis, I'm getting now my theta tilde object. Right? So I get my theta tilde, my blob, and once I get my theta tilde, now I can do exactly the same thing that I did for the TVD algorithm. Then basically the second step is that I'm doing the SVD and then I'm obtain the new MPS. And then we can truncate it. And that's it. So once we are done with this bond, then we just moving to the next bond, to the next bond, to the next bond, and then we just sweep through the lattice until convergence, right? So at each step, the energy is, if you then basically do this iteratively, we can, well, technically it doesn't matter in which order you do it, but in terms of convergence, but you just move really to the left, to the right, and back and forth. And then you just can plot the energy eigenvalues here as function of the iteration, and then what you usually find is at some point it doesn't change anymore, and then you just say that, well, then you just take this as being the ground state energy, as your best guess of the ground state energy, which you then of course have to check in terms of convergence with respect to the bond dimension, etc. But this is how the DMRG algorithm then works. Yes. Yes. And in fact, from the computer science point of view, the algorithm DMRG or the DMRG algorithm, you cannot prove that it will necessarily converge to the ground state. In fact, you can find counterexamples where DMRG would fail. There is also from the computer science community another algorithm which is known where you can prove that it converges. But in practice, it converges slower than the DMRG algorithm. Right? So there's a difference between a typical problem, like a typical condensed matter Hamiltonian, seems to be quite DMRG friendly in most cases, and it usually converges. I mean, there are cases that are getting really difficult, at least from my personal experiences, if you have, for example, random singlet states or something like this, because then there's a structure which is very hard for DMRG to converge to, and very small gaps. Yes. Wait. Yeah, I mean, this is like, right, so what I'm showing here is like really the very basic algorithm where you can, again, use just a few lines of code to write a DMRG code. Then there are tons of improvements that you can do. In fact, as I pointed out, this mixing is a very important thing, like how you grow the bond dimension. By this, you can help the algorithm to get unstuck. If you are suspicious about the structure of the ground state, you can then increase to a multi-site update. You can, yeah, so then it becomes a bit of a witchcraft. No, it prefers, right. So if you have a degenerate state, the DMRG algorithm prefers to find a state that has the least entanglement. And actually, there's a nice example. If you just take, for example, topologically degenerate states, DMRG tends to find the minimally entangled states for the reason that they are best variationally, because they can be represented with the fewest possible Schmidt states. Yes. Oh, the variation is here. This step. So you have now. So the brute force state. I think I have my expectation value. That's the energy. But now I could say that, well, now let me just take out a matrix and let me now find a matrix, like, or some object that I can put in here. I'm just taking out two of them. So now I want to find my object theta tilde such that the expectation value is smaller. Well, the number of, huh? Well, I mean, you could, I mean, one, like, if you don't like linear, again? Yeah, exactly. It's just a, well, but I mean, if you don't like linear algebra, you could also just do some nonlinear optimization of this, but that would be just much harder. You're just finding the minimum of this expression. It's just, yeah, finding the ground state of this effective Hamiltonian. Yes?
And we're trying to find the ground state. Isn't that very expensive because the matrix is chi-square dimensional? And
right. So the matrix, so the matrix that we have here has a dimension of d times chi times d times
this is
squared. Yes.
And then the eigenvalue probably is chi to the power 6.
Wait, but we can use a Lanczos algorithm. So basically, right. So these are kind of technical. So basically, we are not writing this as a full matrix and then do a householder method to diagonalize the full matrix, because we are not interested in the full spectrum of this Hamiltonian at this point. All we are interested in is the ground state. And then basically all we need to do is we need to know how to multiply the Hamiltonian to a state. And then this can be done easier because you say that, well, the Hamiltonian has this form here, right? So this is the Hamiltonian. And now all you want to do is you now apply the Hamiltonian to some theta. Then you have here your theta, and you need to apply the Hamiltonian to this theta. And then you can see that, well, what is the cost? You could say that, well, you have here a chi, here you have a chi, you have d, d. And then in this, like here you have another d, you have a d here, chi. So if I just do it in this way, it would scale then as chi to the power of 4 times d to the power of 4. But this is not the optimal way. You can do it actually smarter by do it successively, right? So you basically just multiply these guys in here. And if you count then the scaling, then you find that this scales as chi to the power of 3. So finding iteratively the ground state of this Hamiltonian using a Lanczos eigensolver, etc., scales as a chi to the power of 3. And that's not too bad. Yes? No. The getting stuck is not happening. At this case, you're not getting stuck. You're going to find the proper ground state of this Hamiltonian in almost all cases. The problem where it might get stuck is because from this iterative thing. So you're at this point, you're finding the optimal state with respect to whatever you have away from here. And this is where the problems start. It's not by finding the ground state of this Hamiltonian. Yes?
Typically, how well does the DMRG work? I not mention that. or
Well, non-fission, there.
How well does it work when I try to search the steady state of the bloody?
Oh no, but then you are just right. So then there are additional problems because if you are looking for ground states of Hamiltonians, if I just say here is the energy. Now here in the middle it's like a continuum, but at the edges, like for the ground state, there's usually not a very dense spectrum, which helps you to actually find the ground state. What? Oh, the question was how well DMRG would work, for example, finding steady states of Lindbladians. And for these steady states, you might find that they're not necessarily as well separated from the rest of the spectrum, which makes DMRG then
real and complex.
Exactly. So yeah, I mean there are several works attempting to use DMRG in this context, but it has shown to be not as simple. Yes.
I'm just wondering, like, when you're doing your update steps, can there be significant like improvement in terms of speed of convergence if you do your updates in different ways than just going left to right, back and forth? Have people looked at this? Like, does it can like make a practical difference?
I'm not so sure. I mean, I don't know a systematic study of this.
Okay.
Yeah, Nushya? Okay, good point. So and in fact, I invite you to play with these tutorials that I uploaded. The variation update is much faster for finding the ground state. So if you are interested in the ground state, you shouldn't use the imaginary time evolution because it takes a very long time to slowly approach the ground state. And the variational update is much faster, like orders of magnitudes faster. Good. So just in because now you can also play with the DMRG code. And in fact, for the DMRG code, I haven't here uploaded a toy code, but I instead want to show briefly how to do this with a software package called Tensor Network Python. And there's if you just Google Tensor Network Python, there's also a website for Tensor Network Python, and there are also simple to look at or like minimal codes for DMRG. So there you can find it. But here I just want to demonstrate how to actually use this DMRG code in a somewhat simple way, so that you don't have to write all the tensor contractions your own. And for this, well, it takes apparently a little bit to install the package here on. But the advantage of using these packages is that they also include all sorts of optimization. For example, it already includes conservation laws, etc., and various different algorithms. But now, okay, so now the package is installed. Then I can load it, and now you see that you don't need to write much code to actually do a DMRG simulation. So this is now for the Ising model. We just first define the parameters, which is now the transverse field, the bond dimension, and the L is now hidden. And now you can define the model parameters. There's a dictionary where you just put in the model parameters, which are the L, J, G. And if you just want to have a finite periodic boundary condition, so here you can just choose the boundary conditions as a parameter, whether you want to conserve quantities or not. So it will automatically, for your model, figure out if it has conservation laws here, but here I don't care about it. And then you can define a model. In this case, it's a pre-made model, which is a transverse field Ising model, but you could also use, you just write your own model, and you can now just choose an initial state, define the parameter for DMRG, and then you just run it. And this is somewhat where you can run it, and then you can just measure measure different observables that you might be interested in. Then it shouldn't take long to get then the results. Yeah, and now you see that well, this is basically the same energy that you get from exact diagonalization, and you just plot the entanglement energy. Good. So I invite you to play around with this. And in the remaining 10 minutes, I actually I was planning to write it on the blackboard, but since I already foresaw that I won't have enough time, I just want to quickly tell you about some algorithmic developments which are more recent, because all that I've talked about so far is between 20 and 30 years old. So now I want to talk about something that's a bit newer. And then this is also, I think, well connected with what's taught in other classes. Here, this is a question about extracting hydrodynamics from microscopic Hamiltonians. And I think you hear more about this next week. But if you want to have the following picture, so let's say that we start from a non-equilibrium state where we just localize all the particles, say, on the left of a box, and now we evolve it in time. And then, according to what we already learned so far, if you just evolve it for a very long time, eventually, assuming that the system thermalizes, you would actually find it's like a thermalized state. So something which is described by statistical mechanics. But then there's some interesting hydrodynamic regime in between where the system has locally thermalized, but then approaches the global thermal equilibrium. And in this time, the equilibration is described by various universal properties. So for example, in many systems you might find that it relaxes and shows some diffusion given by fixed laws, and you just then find that this is governed by some diffusion constant. And you would find, for example, a wave package that you create is decaying proportionally to the square root of to 1 over the square root of t in this diffusion in one dimension. So the question now, and I'm short on time, but basically the question that you might ask is that given a microscopic Hamiltonian, how can you then extract, for example, the diffusion constant d? And then following up exactly what we just played around with, you might say that, well, we just do it exactly by evolving a state. You're just preparing the state, you're evolving it. And then, well, with exactization, you are limited in terms of the system size, and MPS is actually limited in terms of the times that you can reach. So the question how to overcome this. And there's now what you might call a sort of information paradox, because here I'm just plotting the number of bits that you need to store the state, and then here is the time. And from this MPS numerics point of view, we find that the number of bits that you need to represent the state is growing exponentially. So the bond dimension is growing exponentially as function of time. But on the other hand, if you're interested only in local observables, and as we learned from previous lectures also by David Hughes, eventually we expect that the system is described by very few parameters. So you maybe need just a particle density or the energy density, and that will tell you what the local observables are like. And the question is, like, how can we now truncate the entanglement in a way that we do not sacrifice crucial information on observables? And there have been various approaches to this problem in the literature, which I'm listing here. You also find them in the lecture notes. But I want to just discuss one particular one. And given the short time, I just want to give you an idea about what the strategy is. The strategy is to not do the evolution in terms of states, but instead go to the Heisenberg picture and do the evolution in terms of operators. And the evolution in terms of operators doesn't per se not necessarily help you that much, because you would also find that the bond dimension for representing the operator will also grow exponentially, right? So if you just basically take some generic Hamiltonian and you are now looking at sigma x of t, which is e to the minus ith times sigma x on side I maybe, times e to the ith. If you look at the operator entanglement of this will also grow exponentially with time. So that by itself doesn't help. But then we actually were, this is like the thought that we are putting here, that we could say that, well, let us now put some intuition about the problem to actually make life easier. And the idea that we proposed in a recent paper is to actually introduce some artificial dissipation. And the artificial dissipation that we add to the system is that we dissipate complicated operators. we're just defining some super operator, which leaves simple operators invariant. It doesn't touch simple polystrings where we have maybe just a few non-trivial polys. And if there are too many non-trivial polys, we're just exponentially damping those contributions. And the intuition behind this is now the following. If we are interested in, for example, autocorrelation functions between simple operators, so we just maybe want to look at the correlation between sigma x of t and sigma x of time equals to 0, then we can have the following picture. So here we have the time on the y-axis, on the x-axis we have L. L is now the number of non-trivial polys included in the polystrings, and then we can actually say that, well, we start from a simple operator. The operator we start from in this language is a simple product operator where we get only ones, some sigma x, and then just ones. And now we evolve this operator, and then the operator will be a superposition of all sorts of polystrings, also involving very long ones. But these are now truncated. And the assumption that we make is that if you are, in the end, just interested in an expectation value at infinite temperatures for local operators, that the backflow from very complicated operators to the simple operator is small. Then if this backflow is small, then it's actually a good approximation to throw away complicated operator. And by throwing away complicated operators, well, that will reduce the bond dimension. And then we can now come up with an algorithm, which I just want to show, because now that connects nicely to what we did a moment ago, where we say that, well, we have now our MPO that we equivalently can think of an MPS by just bending over the legs, right? So this is now a state on a space where the local Hilbert space dimension is d squared. Then we just do the TBD steps as introduced a moment ago. But then after a small time delta t, we are applying this dissipation. And the dissipation can be nicely encoded into a small bond dimension MPO. And now we have a time evolution. Instead of having the pure unitary time evolution, we have the time evolution, the unitary time evolution, to then every now and then we're doing this dissipation to kill off complicated operators. And if we just now do this evolution and we look at the operator entanglement, so this is now the measure how difficult the simulations are, right? So if we do this simulation without dissipation, this would just keep growing linearly, and the bond dimension growing exponentially with that. So it would get incredibly hard. We couldn't go past this wall. But then if we just turn on the dissipation at certain rates, we see that it actually drops down and it turns into a much simpler operator, which we can then represent with a small bond dimension. But now, yeah, 1 second. But now this is just under the assumption that the backflow is small. In certain cases, for certain random unitary circuits, we can actually show that this is the case. But in general, for Hamiltonian, this is as a leap of faith, and we have to try. But the way that we can try if it works is if we just look at, we just have an exact limit where this gamma actually is going to 0. So what we have to do is we have to do these simulations and extrapolate gamma to 0. And you had a question? Well, the way that the MPO identifies these polystrings is that we have now a basis, like a local basis is 1, x, y, and z. And now you have an operator that you can now basically say that, well, the identity has charge 0, and these operators have charge 1. And now we can have just an operator which is just counting this charge. And this can be done that's a very simple way to be done by an MPO, because you can think of this as being a clock. So you're just going from left to right, and you're just counting whenever you encounter non-zero charge, you're just raising the time up, and then you just have a cutoff. You say that, well, once the time passes NO clock, you just say that that's it, and you just project it onto a 0. Yeah. Yes? Come again? Right, so I mean, I skipped that slide. There are some arguments you can basically think of. this kind of backflow picture. And then parameters that will go into is whether, like, basically the local thermalization time. But there are also many more details to it, because, for example, if you have if you have more complicated conservation laws in this Hamiltonian, so there's no simple answer to this that I would know. Right, so there are a few things. So first of all, these conservation laws are important. So for example, if you have conservation laws that involve n sites or like complicated operator, then you need to make this L star larger than larger or equal to the largest conservation law that you care about. And then there's this local thermalization time. I think that there will be more about this hydrodynamic session in next week. So that there's a certain time scale where you just get a local equilibrium. Yes. Mm-hmm. Only of observability of simple operators. Yes, exactly. So that's, but there's additional thing that basically, if you, I don't know, maybe David should also comment on this if he agrees. But basically, if you just wander off into very complicated state at some point, they are very unlikely to just return back to a simple one. That's basically the context of Philip. No, but that limit we can't do, right? So.
That's why I'm wondering, you know, that does forget that we already did it.
No, we don't. I mean, there's still a leap of faith. So I mean, the best thing that we can do is that we can analytically just know that if, like, for very small gamma, then we expect we have basically that we know that the corrections on the diffusion constant should be linear in gamma, but there's nothing rigorous to say at this point. Yeah, Anusha? Perfect. Yeah, let me just right. So 1 minute. So yeah, right. So this is the algorithm. Just you see elements that you've seen in the talk before, like these brick wall and then these MPOs. And now we can apply this algorithm, right? So one thing that we just show here, so we just first try to push exact diagonalization as far as possible. So here we just look at the mean square displacement from creating some wave package basically in the center, and as function of time. And the dotted line is what we get from this Dewey, or the dissipation assisted operator evolution method. And here we are just pushing exact diagonalization as far as we can. And we see that at least the results look reasonable. So they asymptotically converge to what we get from this method, except there are no limitations on the system size in our method. And then we can now extract for a model the diffusion constant, for example, here for the Ising model with longitudinal and transverse field. We can then look at the energy diffusion, and we can now compare different L stars. So these are the operators that we leave untouched, and it converges roughly to all to the same value. And these are also the values that we found in the literature. And then we can look at various other methods. And this is a paper we are currently writing up, just doing a benchmark comparing different methods for transport. So this is something that you're probably going to hear about next week in this non-equilibrium steady states, and also the cluster truncated Wigner approximation. And one of the key messages that we find is that for non-integrable models, they all agree, but for integrable models that there is some difference. but more about this once we post it, I think. Okay, yeah, I should stop here. Thanks.
the dissipation compared to just truncating the FDO and comparing about the truncation to that?
Oh no, but that would be again that would be a pretty bad idea, because the moment that you just do the truncation, you're just violating all sorts of conservation laws. Like in this one plot that I've shown, for example, if you from this toy example here. Right. No, but like this is the obvious thing where like it would go wrong. But then there's actually a paper that we tried before also together with David, where we were saying that, well, let us now do the time-dependent variational principle, which keeps track of all the conservation laws and extract, for example, the diffusion constant, and it goes wrong. So if you just set off you forcing it to the MPS and only keeping track of the conservation laws, that's not good enough.
Ignore DAOE method you're using. You're tracking the number of non-items.
Yes, that's right.
You have an expectation of like if you're tracking not the number of non-items, but like the rate of it.
Right. So actually, this is one thing that we have been experimenting with, and I basically just punishing things more which are less, which are less local, seems not to help. I mean, like this is one thing that we tried, but this is actually one thing that's still worthwhile exploring. Yeah. Well, I mean, because I think that even though operators are simple, but maybe like you have two Pauli axes far away, they're still fairly likely to return. Yeah. Good. Let me make a quick announcement, because actually there, if you look on this website, so there are these tutorials, and whoever is interested in playing around with these tutorials, maybe after the last lecture today, you can just stick around and then you can ask questions about the tutorials or just work on them here, and I can maybe help out or discuss some questions if you have any.
Hi, Professor Pollmann. I've seen a lot of more.